Hey, good morning, guys. Assalamu alaikum. Sorry for the delay. But yeah, welcome back to grade 12 physics by Inspired Teens, where in today's lesson we'll be starting with work, power, and energy. Work, energy, and power. Okay, so I just want to share my screen. I'm not 100% sure if it is sharing. Try this again. There we go. Okay, cool. So just can you guys please confirm that you can hear me and see my screen and that everything is working fine? Okay, perfect. Okay, just give me one more second to sort something else. Okay, let's hope this works. Okay, I think we're good to go. Sorry once again for the delays. It's just load shedding and I'm not really using my laptop, so it's all going crazy. But nevertheless, let's begin. Okay, so work, power, work, energy, and power, right? So this section, right, it's not that bad, okay? It's relatively compared to other topics, it's not that bad. It's mostly about understanding which formulas you need to use, okay? Which formulas you need to use and when, okay? And understanding that there are many different formulas, okay? What each formula does, what each formula represents, okay? Those are the key things that you need to understand. Okay, so let us begin. Okay, so the first one that we're going to look at is the work formula. Okay, so just give me 1 second. Okay, so the very first formula that we're going to work with is our work formula in joules. Okay, and this formula, so this is work. Okay, work done on an object. Okay, we work with work done on a single object. Okay, and the work done formula is as follows. It's F times delta X times cosine theta. Okay, so firstly, F, of course, is what? It's a force. Okay, a force in newtons. Okay, and more specifically, it is any parallel force. Okay, and it is always positive. Okay, so let us discuss this parallel force thing, right? So let's just go to a diagram below where we have we have a 5 kg box on a flat surface, and it is being pulled by a 40 Newton force, okay, in the upright direction. So firstly, we can note that the direction of motion for this object is to the right. Okay, this object, even though it's pulling up, right, this object is not going to move up. Okay, perhaps there's a person here, okay, who is, that's a very great diagram, but who is pulling this box, okay, to the right. But because it's a person and the box is smaller, obviously the angle of the rope is at an incline, right? So the direction of motion for this object is to the right. Okay, so if you have to ask yourself the question, is the direction of the force in the same direction as the direction of motion? The answer would be no, because the direction of this force is 30 degrees from the horizontal. Okay, so the direction of motion and the direction of the force are not in the same direction. So we cannot call this a parallel force, because in order for it to be a parallel force, it would need to be in the same direction or in the direct opposite direction. So forces in this direction and forces in this direction would be considered as parallel forces to the direction of motion. Because the direction of motion is to the right, a parallel force would have to be a force that's either to the right or to the left. Okay, we cannot have a force that's up or a force that's down or a force that's 30 degrees up. Okay, it has to be in the right direction or in the left direction in order to be parallel to this specific direction of motion, which is to the right. Okay, so just keep that in mind. So what we then do is this 40 Newton force, we separate it into its two components from newtons. Okay, this is the perpendicular version of the force, and this here would be the parallel version of this force. So just say if this is an applied force, okay, this would be the perpendicular applied force, and this would be the parallel applied force. Okay, so now in this case, which is the force that is parallel to the direction of motion? That would be F applied parallel. F applied parallel is parallel to direction of motion, and that's exactly why we call it F applied parallel. Okay, so this is what we need to keep in mind. So when we say that it's any parallel force, okay, any parallel force, we could calculate the work done by it. That's what we mean by a parallel force. Okay, and please do note that two things. The first thing is only parallel forces do work. Okay, so work on an object is only done by a parallel force. If it's a perpendicular force, perpendicular forces do not do work. Okay, they do not do work on an object. Okay, so just keep that in mind. Okay, so yes, when we have to substitute a formula into this work equation, it has to be a parallel force because perpendicular forces don't do work. So any parallel force would do work. Okay, so we've worked with this. It's a force, number one. We're working with any parallel force, number two. Number three, it always has to be positive. So irrespective of what type of force you're substituting, even if it is frictional force, because we know that frictional force will always be a negative force because it will always oppose the direction of motion. So it will always be considered as a negative force. However, even though that will always be considered as a negative force, we will always substitute a positive. We'll just get rid of the negative and put a positive irrespective. Okay. And the direction of the work done is determined by this guy, which is the next thing in this formula, cos theta. Okay. And cos theta has two options. It can either be 0, well, for theta, can either be 0 or it can be 180. Okay, what does 0 represent? 0 represents, tells us that the object is moving in the direction of motion. And 180 tells us that it's moving opposite to the direction of motion. Okay. Yeah. Okay, so when we have an object that is moving in the direction of motion, okay, we will use cosine 0. When we have an object that is moving opposite to the direction of motion, we will use cosine 180. Okay, and if you do the calculation, if you put in your calculator, what is the value of cosine 0? You will see that the value of cosine 0 is 1. And if you put into your calculator cosine 180, you will see that the value of cosine 180 is -1. So this is what helps us to determine direction by either multiplying this entire thing by 1, which won't change it, or multiplying it by -1, which won't change its magnitude, but will just make it a negative, which indicates negative direction. Okay, so yes, for the force, you never substitute a negative. This is the guy that handles the direction. Okay, this cosine theta, where what are our options for theta? What is theta? Theta is, we use it as 0 degrees when the object is moving in the direction of motion, and we use it, we use it in 0 degrees when the force is in the direction of motion, or we use it as 180 when the force is opposite to the direction of motion. Okay, then let's move on to the next the next formula. That's a possibility for this section, and it is work energy theorem. Okay, so the formula that we get from work energy theorem is W net is equal to delta EK. And if you take note of the definition is something like the net work done on an object is equal to the object's change in kinetic energy, and that comes directly from this formula, right? You can see that the net work done on an object is equal to the object's change in kinetic energy. Remember, delta represents change. So again, what do each of these things represent? Firstly, W net is net work done. Okay, so the net work done utilizing this formula that we just used, okay, we can represent the net work done using this formula. Okay, that's the first way we're going to do it. So we're going to have a force times delta x times cosine theta. However, because it's net work done, the force that we're going to use is net force. So F net times delta x times cosine theta. Okay. Another way that we can represent net force is by simply adding all the forces, by simply adding all the work done onto the object, okay, adding them all up. So because this is net work, it's like the total work done. So by adding up all the work that's done on that object, you would get the total work done on that object. Okay, I hope that makes Hope that makes sense. Okay, just 1 second. Okay, cool. Okay, so I hope that's making sense so far. So the first way to represent W net is by utilizing the basic work formula, and the force that you substitute is F net. That makes sense. F net W net, right? So if you're going to substitute the net force into the formula, it's going to give you the net work done. However, like I just explained, another way is by adding up all the work on that object that's done. So let's just say we have an applied force that does work. So we can say work done by the applied, plus work done by the frictional force, plus work done by the gravitational force, and all the forces, whatever forces act on that object. Okay, you can calculate the work done by those forces and just put it in an algebraic sum and add them all up, and that would give you the net work done. Okay, remember, of course, some would be negative, or this one, for example, would be negative, and then you'd be subtracting because it would be a plus minus, whatever it is, but you're just adding them all up. So this is the second way that W net could be broken up. And the third thing we need to discuss for this is delta EK. So firstly, we need to know that, remember, EK itself is half mv squared. Delta EK is the change in kinetic energy. So EK final minus EK initial, right? So it can be broken down. Its formula would be half mv final squared minus half mv initial squared. Okay, you can take the common factor of half m if you'd like and represent it slightly differently. V final squared minus V initial squared. Okay, please remember that you need to square this. You need to square your final and your initial separately. You're not going to get the same answer if you square that. Okay, please just keep that in mind. If you ignore those or forget those and square this whole thing, you're not going to get the same answer. So please remember to square them each individually if you use utilizing that short version of the formula. Okay, so we've learned two things so far. The first is work. The second is work energy theorem. So the first is the basic work formula. Okay, just F times delta X times cosine theta. And then the second is the work energy theorem. And we learned about its formula and what are each of its components. Okay, right, let's move over to the next one. Okay, let's move over to the next one, right, which is arguably, in my opinion, the most important one we need to go through. And you'll see that you can probably get through this section, okay, with just these formulas. Okay, so the third and final thing, not the final, the third thing, right, of the formulas that we need to learn fall under energy principles. Just 1 second. All right, so sorry about that. So yes, so you might, I don't know if you might have been confused with what falls under energy principles, what doesn't fall under energy principles, or sometimes you see the reason we need to know the names of these formulas is because sometimes they'll tell you use work energy theorem to solve for this, or use energy principles to solve for this. Okay, so if they say use work energy theorem, you can use that. Okay, well, you need to use that. If they say energy principles, you need to use this, or you need to use this. Okay, so when it comes to the final exams that you guys are going to write, when they say use work energy theorem, so just say you get to a question and they tell you use work energy theorem, please note that you are not restricted. Even though they tell you to use it, you are not restricted to only use work energy theorem. If you look at certain memos, especially for final papers, you'll see that in the memo, they will have the solution solved with work energy theorem, with energy principles, or with whichever method is possible. So when they say use work energy theorem, you are not restricted to using it. You can use a different formula. However, when they say use work energy theorem, or whichever one they say, maybe they say use energy principles, okay, that's just, you can take that as a hint to say, okay, I definitely can use, because they're telling me to use energy principles, I know that a possibility, I definitely can use energy principles. Okay, so it gives you like a hint. Okay, so keep that in mind. If you are stuck and if you don't know which formula to use and they say use energy principles, you know, okay, I definitely can use energy principles, so let me try that. Okay, however, again, you're not bounded to only use work energy principles, even though they say use energy principles. Okay, that's for like the final exam. Now, when it comes to your class tests, it really just depends on how strict your teacher is. Okay, so you need to find out from your teacher. Okay, so don't take it as what I said for the final exams as true for your own class tests. So whichever test you write leading up to the finals. Okay, so just keep that in mind. Okay, so let's move on to energy principles. So energy principles, we have two different formulas. The first formula is the conservation of mechanical energy, and the second formula is for non-conservative forces. Okay, so conservation of mechanical energy, the formula for that is that the mechanical energy at a certain point is equal to the mechanical energy at another point. The mechanical energy at A is equal to the mechanical energy at B. Okay. And what is mechanical energy? Mechanical energy is actually the sum of the potential energy and kinetic energy. So that's why we further simplify these formulas as follows. Okay, so the mechanical energy at A can be represented by the sum of the potential and kinetic at A, and then the mechanical energy at B can be represented by the sum and potential at B. Okay, so remember, potential energy can be simplified as mgh, mass times gravitational constant times height or gravitational acceleration, and then kinetic energy, we went through it, half mv squared. Okay, so it's the same for both of them, but just at different points. Now, the biggest criteria in order to use this information is that you have to have an isolated system. Now, what does it mean to have an isolated system? Having an isolated system means, number one, okay, that you have no frictional force. Number two, okay, you have no applied force. And no tension, which is very similar to applied. Okay, so you have none. In order for you to have an isolated system, you have none of these three things. Okay, the main one is that you don't have frictional force. Okay, that's the main one. But yes, all of the others are just as important. The main one, you don't have frictional force. However, like for example, if you have a system that does not have friction, but has an applied, it is not an isolated system. In order for it to be an isolated system, there needs to be the absence of these three forces: frictional force, applied force, or tension force. Any sort of applied force, any sort of tension force. Okay, please note, if you have a frictional system, a frictionless system, meaning a system with no friction, however, there's an applied, then it's not an isolated system, and you cannot use conservation of mechanical energy formula. The only time you can use the conservation of mechanical energy formula is if it is an isolated system, meaning there's no friction, there's no applied, there's no tension. And then, okay, you can go ahead and you can use this formula to try and help you calculate whatever it is you need to calculate. Okay, keeping in mind here we have mass and height that's involved. Here we have mass and velocity that's involved. So if it's a velocity you're looking for, then yes, perhaps you could use this formula, but we'll get to examples to explain that, right? So when, yes, so when can you generally use this formula, conservation of mechanical energy? In the absence of friction, generally. Okay, you'll see, I'll explain to you what my thing is for the section. In the absence of friction, you can utilize this formula. There definitely needs to be an absence of friction. Okay, then let's move over to non-conservative force formula. The non-conservative force formula, it includes all forces except Fg. Okay, so what are non-conservative forces? Non-conservative forces include all forces except Fg, and Fg is the only conservative force that we work with. Okay, so the only conservative force that we have is Fg. Okay, and everything else is a non-conservative force. Okay, so a non-conservative force is defined as, it's in the examination guidelines, which I put in the Google Drive, but it's something like the non-conservative force is defined as a force that acts on an object where that force is dependent on the path taken by the object. Okay, and a conservative force is where the force on an object is independent on the path taken by that object. Okay, and that's why Fg, okay, Fg is not dependent on the path. Fg is dependent on gravity. Okay, it depends on the type of gravity, depends on which planet you're on. Okay, and the extent of the gravity. Okay, so how can we break up this formula? Let's explain this formula. So WNC is equal to delta EP, meaning change in kinetic energy plus change in potential energy plus change in kinetic energy. So WNC, okay, is basically now all the non-conservative forces, the work that they do on the object. So we could break this up as work done by frictional force plus work done by perhaps applied force, right? Whatever the forces are on that object, you just add them up, provided they are non-conservative forces. Okay, so this formula is amazing, and it's really my favorite formula. Okay, and I'll tell you why, is because this is work done by non-conservative forces, right? However, so you would think like, okay, this formula, I use it when I have non-conservative forces. However, you can even use this formula when you have no non-conservative forces. So let me explain to you how you can use, so this says using WNC with no non-conservative forces. Okay, now how can you use it? I'll give you an example of when you have no non-conservative forces. So let's just say we have a 5 kg box. Okay, and this 5 kg box is just flying in the air, right? It's just going down. Okay, it's just free floating in the air, and it's just going downwards. Okay, with the absence of friction. Okay, so no non-conservative forces, right? It's just going in the downward direction where the only force acting on it is Fg. Perhaps we're foreshadowing for vertical projectile motion. Did we do that already? I don't know. But anyway, it's going in the downward direction. So in this case, now how could you use WNC? So WNC is equal to delta EP plus delta EK. Okay, so in this case, we have that the non-conservative, this is the formula, the non-conservative forces is equal to the change in the potential energy plus the change in kinetic energy. And all you can simply do then is equate this to 0. Since there are no non-conservative forces, this formula, the change in potential energy and the change in kinetic energy, should equate to 0. Okay, so you can even use this formula when you don't have any non-conservative forces. You just equate it to 0. And an example for that is here. When you have an object that's just free falling and you ignore friction, just ignore friction. Okay, so the only force acting on this object is gravitational force, which is Fg. And Fg is not a non-conservative force. Fg is a conservative force. Remember, Fg is the only conservative force that we work with. Okay, so yes, there's no non-conservative forces, so you can even use this formula, but equate it to 0. Okay, so this is a very, very versatile formula. Let's break up EP. I'm going to write the short version one time. I'm taking the common factor of mg, because remember, we work with one object, so the mass stays the same, right? And then the final height minus the initial height. Okay, that's the change in potential energy. What about the change in kinetic energy? Half m. Again, we work with one object. V final squared minus V initial squared. Please remember that they are each of them are separately squared. Okay, not the whole bracket squared. Okay, so that makes sense, right? So a hint to use this formula is when we have friction. When friction exists. Let's maybe do it in green to understand. Okay, when we have friction, we use this formula. Okay, so now before we move on to the next part, and before we move on to do a question, let me just explain these two formulas and why they are so brilliant. Okay, these two formulas can be used for majority of the questions that you need to solve. these two formulas can be used for majority of the questions that you need to solve. Okay, so this is what I want you to do. Okay, if you're still new to the section, or even if you have practiced the section, right? Whenever you are doing a question, okay, you ask yourself two questions. Does the question or does the system in the question have friction, or does it not have friction? If it has friction, then the first formula that I want you to try, the first formula that should come to mind is this guy. Non-conservative force. When there is friction, the first formula that should come to mind, the first formula that you should try is non-conservative force. Now, I'm not guaranteeing you that it's going to work 100% of the time, but for most of the question, I could say 90% of the questions, this formula is going to work when there is the presence of friction. Okay, just keep that in mind. Okay, if it doesn't work, then you can try another formula, okay, such as work energy theorem. Okay, but you're going to see when we try these questions, non-conservative force is going to work. Okay, and then when we get to the question, I'll explain more things that's going to help you. That's going to I attempt to help you in trying to solve these questions, or in order to guarantee you to know which formula you need to use, right? So yes, when there is friction, first formula that should come to mind, this guy, work done by non-conservative force, WNC. Okay, that's what I'm probably going to refer to it now, from now going forward, WNC. Okay, well, the formula for work done by non-conservative forces. Okay, then the second thing is when there is no friction. Okay, but at the same time, so when there is no friction, I want the first formula that you should try to be this formula, conservation of mechanical energy. However, when you check that there's no friction, your second criteria immediately before you. What is going on? Can you guys still see my screen? Yes. Okay. I don't know why it's telling me my screen sharing is paused. Okay. Is it moving? Is my screen moving, or is it paused? Like, is it moving? Like, are you still? Is it showing a question now, or is it still showing the same thing that it was? It's paused. Okay, I have no idea how that happened. Let me reshare my screen. No. Oh, no. Okay. Okay, there we go. Should be working again. Technical difficulties are the most unavoidable thing that has ever existed. It's crazy. Okay, so yes, what were we saying? Okay, we were talking about using energy principles, and we talked about conservation of mechanical energy. Oh yeah, okay, there we go. Okay, we talked that we're speaking about oh yeah. So we're talking about when to use conservation of mechanical energy. So I was saying that when the system in the question has no friction, okay, firstly, before you think what formula am I going to use, it must have no friction, but it must also have no applied and no tension, because you will see questions where there's no friction, but there is an applied or there is a tension. Okay, and in that case, you cannot use conservation of mechanical energy. In that case, you will most likely have to use energy principles, or perhaps conservation of mechanical energy. Okay, you can even use, sorry, not conservation of mechanical energy, WNC. Okay, non-conservative force formula. Okay, in that case, you could even use that, because even though there's no friction, there's an applied, and applied is a non-conservative force. Okay, so you could use in those cases, you could use work energy theorem or non-conservative forces. However, if your question has no friction, no tension, no applied, the first formula that should come to mind that you should definitely try is conservation of mechanical energy. Okay, so these two formulas, they should be the first formulas that you should think of using when you have a question. When there is friction, non-conservative force, actually, you can say when there is friction, applied, or tension, you use non-conservative force. You try out non-conservative force. That's the first one you try. When there is no friction, no tension, no applied, you try out conservation of mechanical energy. And the reason I'm saying you try it out is because, yes, it's going to work for majority of the questions, trust me. But for some reason, if it doesn't work for a specific question, then you can go ahead and try a different formula. Okay, which is work energy theorem. Basically, that's the only other formula that you work with. Okay, let's move on to the next. First, this is just the concept, and then we can go into a question. Okay, so this concept that we have to discuss is the concept of constant speed. Okay, constant speed, meaning when we have a constant velocity. Okay, when we have a constant velocity, firstly, we know that when there's a constant velocity, acceleration is zero. There's no acceleration. There's no increase or decrease in the velocity. Since acceleration is zero, according to Newton's second law, F net is zero. Okay, and then since F net is zero, remember, W net would be zero because F net gives us W net. So W net is zero. Okay, and then since W net is zero, EK is zero. Okay, there's multiple ways you could go about it. Since velocity is zero, EK is zero, half m0 squared, because half mv squared. Since EK is zero, W net is zero, and so on. But we just need to memorize that all of these things are zero when we're dealing with a constant speed, okay, or constant velocity. Okay, I think we might have went through this when we did Newton's, but nevertheless, we can just go through it again. It's a little silly diagram that tells you when there is friction or the existence of friction. It might look obvious, okay, but it's not always so obvious. And just to make sure that you are certain whether there's friction or not, maybe the question is ambiguous, especially sometimes in like a prelim paper, they can be ambiguous. Okay, so the existence of friction, how do we know that friction exists? Okay, so with these, one of these, the thing about this is only one of these points can be given, or multiple can be given, right? But the confusion might be when one of them is given, right? If mu k is given, so if they don't tell you it's a rough surface, or if they don't tell you, or they don't show you in the diagram it's a rough surface, or they don't tell you friction exists, if they give you mu k, then you should just automatically assume that there is friction. Okay, that's the first thing. The second thing is if they tell you there's friction, okay, then there's friction, obviously, right? If they say it's a rough surface, okay, if they say it passes from A to B, which is a rough surface, then you know, okay, that's friction. Okay, or the diagram shows a rough surface like shown below. Okay, rough surface or a little squiggly line to indicate a rough surface. Okay, cool. Let us move on. I think we need to do this one first. Okay, it's been a while since I've solved the question, but let us do this question. Okay, an object moves up an inclined plane with an initial velocity okay, no, let's not do this question first. We have to do this question first, sorry. Indubitably. Okay, perfect. Okay, so 1 second. There we go. Okay, so the diagram below, not drawn to scale. By the way, we're going to end it. We're going to end slightly late, around 20 past, just so we can get an hour done. Okay, the diagram below. Wait, normally we end at 5 past, so we'll end at around 2. Okay, let's just see. Let's try and get a question done, right? The diagram below. Okay, so also just by the way, for those of you who need to leave, right, because we have scheduled till 10 to 9 or 9 o'clock. If you want to, you are free to leave, and then you can catch it up later. Okay, but for those of you who can stay, I recommend you stay, please, so you can benefit. Okay, the diagram below, not drawn to scale, shows a trolley of mass 38 kg released from rest at point A on an incline. ABC is a frictionless section and CD is a rough section of the incline. The trolley reaches point B of the incline at a speed 1.5 meters per second. Okay, so yes, the usual important stuff I will repeat. Whenever you are going through a question, whether it's maths, whether it's physics, whether it's chemistry, okay, mostly maths and physics, any information that is in the written, okay, you want to take it out of the written and you want to put it neatly into the diagram so that you don't have to keep referring back to this long paragraph to look at information, right? Remember, you're on a time limit, okay? Your examination is timed. You need to try and be as fast as possible, of course, okay? So all that information that you read, you need to read it once, and then you take all the information that's important, that needs to be known, and you slot it into the diagram, and that way all your information is in the diagram. So all the important information, what you can also do, perhaps, is you can highlight it as you're going along. You're like, okay, the diagram below on a Toronto scale shows a trolley of mass 38 kg is released from rest. Okay, that's also important. Why is that important? That is extremely important that you need to know that it's released from rest, because if it's released from rest, then here, this V initial here is 0, or its velocity doesn't have to be an initial, it's 0. Okay, so that I'm done. I put that into the diagram. 38 kg was already in the diagram, so I don't need to put that. At point A on an incline, ABC is a frictionless section. Okay, ABC. Okay, so I know that this entire thing, now this maybe you don't have to put like such a fancy thing, but I know from A to B to C, what I like to do is I just like to put smooth. Okay, and take a thin highlighter, or you can put that thin part of the highlighter and just highlight this part so you know that this entire part we're talking about is smooth. Okay, and then they say, let's go back to this diagram. Then they say, and CD is a rough section of the incline. So then you take a different color highlighter. Okay, if none of this confuses you or whatever, then you don't have to do these things. Sometimes it makes life a bit easier. This is a rough surface. Okay, they even indicated it on the diagram, and they made it a bit more squiggly and a bit more bold. Okay, but just so it's easier to understand, right? You're doing this thing in literally like 30 seconds, right? You're just taking all these things down so that you know it's easier for you to reference back to your diagram. Okay, then they say what? Then they say incline, the trolley reaches point B of the incline at that speed. Okay, that I already put there. So at B, it's 1.5 meters per second. Okay, cool. So now all that information, like literally this could be ignored. It's gone. Everything that I need, I put it into the diagram. Now I can work going forward. 5.1, define the term non-conservative force. Do I have a definition? Yeah. Okay. Let me get you guys an exact definition. What's the fastest place to get that? Go to your Google Drive and let's utilize that thing. Okay, examination guidelines. Work, power, energy. Conservative force, what do they want? Non-conservative. A non-conservative force is a force for which the work done in moving an object between 2 points depends on the path taken. Examples are frictional force, air resistance, and tension in a cord. Okay, so it's similar to what I said, but they just give you a fancier definition. Basically, there we go. Basically, yes, it's the force done on a moving object is dependent on the path, right? That's why we say the only non-conservative force that we work with is actually gravity. Gravity that doesn't depend where you are, what you're sitting on, what type of surface is, or what type of surface anything is. It just solely depends on gravity. Okay, so it's independent to the path. Okay. Name the non-conservative force acting on a trolley or acting on the trolley. Okay, so this question is a bit weird because from A, B to C, there's no non-conservative force acting on the trolley. It's actually from C to D. And the non-conservative force acting on the trolley from C to D is the frictional force. Okay, then they say point C is a point on the incline 0.5 meters lower than point B. Okay, so point C is 0.75 meters lower than point B. Calculate the speed of the trolley when it reaches point C. Okay, calculate the speed of the trolley when it reaches here. Okay, so just two things to note. Okay, so we know that from the whole ABC is a frictionless surface. Okay, so since we don't know the height of A, okay, remember A also has a height, because we know one piece of information about A. Okay, we know that A, okay, the initial velocity there is 0 because it was released from rest. Okay, that much we know, but we don't know the height at A. However, we know the speed at B and we know the height at B. So in this question, the telling us that it was released with the speed of 0 is actually useless, which is annoying because you generally don't think that any information is useless. But after a little bit of analysis, you realize, okay, I don't actually need to use that because I don't know the height here. Okay, I can't work with it. I need to know the height and the velocity in order to work with it. So, right, before we get anywhere, right? So we're only going to work from B to C. I just wanted to clarify that. Now, the thing I told you, the advice that I told you of now, what formula do I use? That's the question. That's the tricky part where everyone's now confused and crying. Okay, but you know that from B to C, there is no friction. Then you double check there's no applied and there's no tension. Yes, from B to C, it's just a cable car, or it's a trolley that's falling down. So the only force acting on it is what? The only force acting on it is gravity. There is no friction, no tension, no applied. So we said when we have that type of scenario, what's the first formula that should come to mind? Energy principles, conservation of mechanical energy. So that's exactly what we're going to do. Okay, so 5.3, and we're going to further analyze this, right? 5.3, conservation of mechanical energy says that Emac at A is equal to Emac at B, and then we can separate it, right? The potential energy at A plus the kinetic energy at A, we can just do this, is equal to the potential energy plus the kinetic energy at B. Let's further break this down into the formula. We have mgh plus half mv squared at A is equal to mgh plus half mv squared at B. So the second thing you can check, so that's the first thing, right? My advice to you, when there's no friction, no tension, no applied, conservation of mechanical energy, that's the one you go for first, that's the one you try. Now, what can further confirm that for you? Let's look, what are the variables inside of the conservation of mechanical energy formula? We have height, okay, because mass, yes, mass and height. Mass is normally a common thing that's given, right? But you double check it for it as well. There's no harm in that. We have mass and height. Okay, that's two things that we need to either want to calculate or either have values for, mass and height. And if you look in this question, we have heights. Okay, we'll discuss the height of C in a bit. We have heights. We have height of B and height of C, right? So we have heights. Then there's velocities. Okay, again, half, that's a constant. Mass, we have as well. And velocity. Okay, yeah, you double check. Okay, do I have mass? Yes, I do have mass. That's fine, right? Since it's for one object, if you have the mass, done. All the masses in all your calculations sorted. I have heights. I'm working with heights. That's fine. That's in conservation of mechanical energy. And velocities, that's also in conservation of mechanical energy. The first velocity is known. The second velocity is what they want us to calculate. So yes, this formula is making sense. So that's the second thing that you can double check in your mind to be confident that this is the right formula that you're going to be using. Okay, so let us continue. Let us talk about heights. Okay, so we know that here is the ground. Well, if you don't, now you do. This is the ground, right? Now, when we talk about h in our formula, it is normally what? It is normally the height above the ground. However, it does not always have to be the height above the ground, and I'll tell you why. So basically, okay, it does not always have to be the height above the ground, because if it had to be the height above the ground, then technically we would not know the height of B, and we would not be able to do the calculation, because the height of B, we don't know the height of B above the ground. We just know the height of B above C. We just know the height of B above C. The height of B above C is 0.75. Okay, and then C, we would take its height as 0. So it's almost like we take a new reference point of the ground. Okay, the new reference point of the ground is C. It's almost like C is the ground, and this would work. Do not worry about it. This would work 100% of the time. Okay, taking another point as the ground reference point and then calculating the height of the second point above that ground reference point, that would work. So we know the height of B as above C as 0.75, so we can use the height of B as 0.75. It just means that now we don't use the height of C as the height above the ground. We just use C as the ground. Okay, because we know the height of B above C, it's almost as if C is the ground. So we use the height of C as 0. Okay, so that's important. I hope that you guys understand. If you do not, please let me know, and then I can go through that again. Okay, but that's important. So let us solve it now. Okay, so I hope I remember things. This is 38. G is 9,8. Okay, that's a constant. Now we're talking about at A. Okay, so what is at A? Okay, at A, normally you put the first position it's at, and then B would be the second position it moves to. Okay, so we would consider B in this case as A. Okay, this is our first point, this is our second point. All right, so at our first point, its height is 0.75, its speed is 1.5. Okay, so the height is 1.75. All right, so no, 0.75, I think. Yeah. Okay, we don't have to actually have these brackets. Okay, plus half, its mass is 38, and its velocity at that point was 1.5 squared. Please do not forget to square it. I always forget to square it. Okay, then at C, we have a mass of 38 that hasn't changed. Gravitational acceleration of 9.8 that hasn't changed, but now the height at C is going to be 0. Okay, just keep that in mind. Height at C is going to be 0. So technically, you actually, if you don't want to, you don't have to even write any of this out. If you know the height is 0, automatically you can just write 0. Okay, plus half, its mass is 38, and its velocity at that point is actually what they want us to calculate, the velocity at C. So what I'm going to do is replace A and B here with C and B and C. Okay, because that's like the actual point you're working with, the velocity at C squared. That's what they want us to calculate. Okay, now it's just algebra, right? Okay, sorry, I'll be back in 1 minute. So you guys can try and do this calculation. I'll be back in like 20 seconds. I just need to switch off something. Okay, cool, right? So yes, this is now just algebra. So please don't mess up on the algebra. What I would recommend, perhaps, you see, because you don't want to get weird numbers. I don't think you're going to get weird numbers here, right? Ultimately, you don't want to get like 500 decimals and then you have to write those 500 decimals, because you don't ever want to round off until your last step, right? You want to keep all exact values until your last step. So maybe do this whole thing in your calculator. If you're not comfortable with that, do this and then add it to that. You can even use the feature in your calculator that the ANS feature. So you do this in your calculator, then just say ANS plus this, and then we can take it from there. So let's simplify the left-hand side first. So I'm going to say 38, 9.8, 0.75 equals, I get an answer, then I say that, plus, open brackets, a half, 38, and 1.5 squared. Okay, so this, for this entire left-hand side, I'm getting an answer of 322.05. This is equal to, we can simplify this right-hand side. So I can have a half times 38. That's going to give me 19 v at C squared, or v final squared, doesn't really matter. Divide both sides by 19, or take 19 over as a division. Okay, so I have 322.05 divided by 19. And I'm getting 16.95 is equal to VC squared, square root both sides to get rid of the square there. And you're going to get an answer of square root answer. The velocity there is 4.11, 4.12, and you simply round off to 2 decimal places. So again, I'm only rounding off to 2 decimal places at the end, meters per second to the minus 1. Okay, so or alternatively, if you're super comfortable with it, do it all in one step, however you're comfortable, but please do not round off until the end and do not mess up the algebra. You don't want to study and work hard in physics and to work hard to understand everything in physics just to mess up the algebra. Okay, so let's give me 1 second. Let me message in the next group. Okay. So yes, that's our final answer. Okay, so how did we decide on that formula again? Frictionless surface, no friction, no tension, no applied. So therefore, we utilized energy principles and we got the answer. Okay, let's look at for answer 5.4 now, but there's something to read before we carry on. So just also note that like whenever you have paragraphs of explanations after questions, it only applies for the next question. Okay, don't think that this applied for 5.3, for example. The coefficient of kinetic friction between the trolley and the surface for section CD is 0.21. The trolley comes to rest at point D. Okay, so very important information in this thing. We know mu k 0.21, mu k for CD. Okay, we also know that the trolley comes to rest at point D. So the final velocity here, or just the velocity at D, is equal to 0. We can even now put the information that we just calculated into the diagram, which is that the velocity at C is 4.12. Okay, now we know the velocity at C is 4.12. And then we know that the final one at D is 0. Yeah, okay, that's all the extra information. And then mu k, if you want to write it, you may. Mu k is equal to 0.21. Okay, now calculate the magnitude of kinetic frictional force on the trolley as it moves from point C to D. Okay, 5.4. Calculate the magnitude of kinetic frictional force acting on the trolley as it moves from point C to D. This sounds like a little bit of newtons. Yeah, this is a bit of newtons. Okay, nevertheless, let's do this calculation. So 5.4, they want us to calculate frictional force. So remember, frictional force Ff is equal to Fn times mu k. Okay, so mu k we know, Fn is the one we need to calculate. Okay, so if you remember correctly, Fn, the way we calculate Fn is we say the up forces are equal to the down forces. Okay, and then how did we calculate that? We had to do a free body diagram. So let's do a free body diagram for this guy. So I'm just going to do it quickly. So we have Fg. Okay, we have Fn. And then we have friction going up. I think that's about it. Okay, so now what I'm going to have to do is separate Fg into its components. We have a Fg perpendicular, and we have an Fg dotted lines. We have an Fg parallel. Okay, now I must get rid of this. Can't have both. Okay, now up forces are equal to down forces, and in this case, I can see that Fn is equal to Fg perpendicular. Okay, on an incline, we remember we can generalize for Fg perpendicular. So let's just say up forces are Fn is equal to Fg perpendicular. We can generalize that Fg perpendicular is equal to mass times gravitational acceleration times cosine theta. What is theta? Theta is the angle of inclination of the surface. This is given as 10 degrees. Angle of inclination of the surface is given as 10 degrees. And I'm going to get a normal force of 366,74. This is in newtons. Now the frictional force is equal to 366,74 times 0,21. And we're going to get an answer of a frictional force. Where's my answer? Okay, it's fine. Let's just do the calculation. 366.74 times 0,21. If there's anything wrong, please let me know. 77,02 newtons. Yeah. Okay. So that's how I got my friction. Okay. So that's a little bit of newtons. Let's look at 5.5. We won't complete it because we don't have time, but we can just have a look at it. Now, 5.5, it says use energy principles only to calculate shame. Only, eh? Use energy principles only to calculate height h. Okay. So we don't actually have to use energy principles. That's just the first thing. Okay. We don't have to use energy principles, but we are going to. The reason we are going to use energy principles is because I told you, okay, that whenever there is either friction, tension, or applied force, we're going to, okay, mainly friction actually. When it comes to W and C, mainly when there's friction, when there is friction, you are going to try to use W and C. Okay, so that's what we're going to use. And remember, W and C is part of the energy principles. There's two that fall under the energy principles. One is the conservation of mechanical energy. The other one is work done by non-conservative forces. So WNC is equal to change in potential energy plus change in kinetic energy. Okay, and that's where we are going to leave it for today on a cliffhanger. When we come back next week, we will finish up this question and I will show you. So it's great, actually. We've done all the things of this question, of this section, like the theory. So this week we did a basic question for 5.3, just it's actually one of the most common calculations that you're going to be doing in this section, conservation of mechanical energy for like smooth surfaces, right? So yes, we did a basic calculation on that, and we did some newtons, unfortunately, and we got to a point where we are now going to use WNC, which again, two of the most common formulas that you can potentially use, and we'll do that next week, and then we'll move over to a different question. But yeah, thank you guys so much for joining. Sorry for all the technical issues today and for all the delays, but I trust that you guys were patient. I will see you guys next week again when we'll continue with all of this. Okay, unfortunately, there's no time to leave it for questions because we are late, but I will see you guys next week. Thank you guys so much. Jazakallah khair. Assalamu alaikum.